We stand on a planet 4.5 billion years old, convinced we are the first to look up at the stars and wonder. But what if that certainty is an illusion? What if ancient cities once stood on Mars when it still had oceans? What if beneath the crushing clouds of Venus lie the remnants of a world that died before Earth even had multicellular life? What if we are not the pioneers of consciousness in this solar system, but merely the latest chapter in a story written and erased 1,000 times over? The evidence we expect to find might have vanished 1 billion years before the first dinosaur drew breath. And in that silence, in that vast and terrible absence, lies one of the most haunting questions science has ever dared to ask. If you love deep space deep dives, you can subscribe. It helps more than you think. The solar system is old. Not old in the way a mountain is old, or even in the way the pyramids are old. It is old in a way that breaks human intuition. 4.5 billion years. To put that in perspective, if you compressed the entire history of the solar system into a single 24-hour day, modern humans would appear in the last 2 seconds before midnight. Recorded history, everything from the first cities to the Apollo missions, would occupy less than the final 10th of a second. We are an afterthought in deep time, a whisper at the end of an epic no one remembers. And yet, we assume we are the first. We assume that in all those billions of years, across all those worlds and moons, no other intelligence ever emerged, built, wondered, and disappeared. That assumption might be the most extraordinary claim of all. The idea that we might not be the first technological civilization in our own cosmic backyard sounds like science fiction, and for most of human history, it would have been dismissed as exactly that. But science has a way of forcing us to confront uncomfortable possibilities. In recent years, a small but growing number of scientists have begun to ask the question seriously, not because they have found evidence of ancient alien cities, but because they have realized how little evidence would remain if such civilizations had existed. The universe does not preserve history the way we do. It erases it, grinds it to dust, melts it back into the furnace of geological processes. And once you understand how thoroughly the past can be destroyed, the question stops being whether ancient civilizations could have existed without leaving a trace, and starts being whether we would even know where to look. Consider Earth itself, our own planet, the one we know best, the one we have studied for centuries. We think of it as a library of the past, a place where fossils and rock layers tell us the story of life stretching back hundreds of millions of years. But that story is incomplete, catastrophically incomplete. Plate tectonics, the grinding movement of continents, recycles the ocean floor every 200 million years, or so. Subduction zones drag ancient crust back into the mantle, where it melts and is reborn as something new. Mountains rise and erode, coastlines shift, sediments bury what came before. The surface of the Earth is not a stable archive. It is a palimpsest, written and rewritten, with older layers scraped away to make room for the new. Go back 500 million years, and the continents were not even in the same configuration. Go back 1 billion years, and the rock record becomes sparse, fragmentary, unreliable. Go back 2 billion years, and whole chapters of Earth's history exist only as faint chemical hints in ancient minerals. Now imagine a civilization that rose not millions of years ago, but hundreds of millions, or 1 billion. What would remain? The answer is almost certainly nothing that we would easily recognize. Cities would erode, metals would oxidize and disperse, plastics would break down under ultraviolet light and microbial action. Even our most durable creations, things like radioactive waste or certain synthetic molecules, would eventually be buried, scattered, or transformed beyond recognition. In 200 million years, when the ocean floor we know today has been completely recycled, how much evidence of our civilization would remain? Perhaps some odd isotope ratios in sedimentary layers, perhaps traces of industrial pollutants in ice cores that might still exist in some frozen corner of a future Antarctica. Perhaps certain minerals that do not form naturally, but no buildings, no roads, no satellites, except perhaps a few in very high orbits that might persist as debris for a few 100 million years before their orbits decay or they are pulverized by micrometeorite impacts, we would be gone, almost entirely gone. And if we would be gone, then so too would anyone who came before us. This is the foundation of what is called the Silurian hypothesis, named somewhat playfully after a species of intelligent reptiles from the British science fiction series Doctor Who. The hypothesis was formalized in 2018 by astrobiologist Adam Frank and climatologist Gavin Schmidt, and it is not a claim that ancient civilizations existed on Earth. It is a thought experiment, a challenge. If an industrial civilization had existed on Earth tens or hundreds of millions of years ago, what traces would it leave, and could we detect them? The answer they arrived at is humbling. We probably could not find direct evidence like fossils of technological artifacts, but we might find indirect evidence. Anomalies in the geological record, spikes in carbon isotopes that suggest massive, rapid burning of organic material, unusual concentrations of rare earth elements or synthetic chemicals, thin layers of sediment enriched in plastics or heavy metals. These would be subtle, ambiguous, easy to misinterpret, but they would be there if you knew what to look for. And the uncomfortable truth is that we have barely begun to look. The Silurian hypothesis forces us to confront a deeper question. If Earth, with all its dynamic geology and churning crust, could erase a civilization in a few 100 million years, what about worlds that are geologically dead? What about planets where the surface has not been recycled, where the past lies frozen in place, waiting? What about Mars? Mars is smaller than Earth, colder, more distant from the sun. Today it is a desert, a frozen wasteland, with an atmosphere so thin you could not breathe it, even if it were pure oxygen. The surface is bombarded by radiation, scoured by dust storms that can engulf the entire planet for months at a time. It looks dead, and by most definitions, it is. But Mars was not always like this. Billions of years ago, in the first billion years of its existence, Mars was a different world. It had rivers, it had lakes, it almost certainly had an ocean covering much of its northern hemisphere. The evidence is written into the landscape. Dried river valleys snake across the surface, carved by flowing water. Deltas fan out where rivers once emptied into ancient seas. Minerals that only form in the presence of liquid water lie scattered across the Martian surface, detected by rovers and orbiters. For perhaps a few 100 million years, maybe longer, Mars had liquid water on its surface. It had a thicker atmosphere, it may have had rain, and if it had all of that, then it is not absurd to wonder whether it had life. And if it had life, could that life have become complex? Could it have become intelligent? The timescale matters. Mars lost most of its atmosphere around 3.5 to 4 billion years ago, after its magnetic field shut down and the solar wind began stripping away the gases that kept the planet warm. But before that, there was a window of a few 100 million years, perhaps as long as 500 million years, when Mars might have been habitable. On Earth, life appeared remarkably quickly, within the first few 100 million years after the planet cooled enough to have liquid water. If the same processes that led to life on Earth could occur on Mars, then life might have arisen there too, during that ancient wet period. And if life arose, it had time, hundreds of millions of years. On Earth, it took about 3.5 billion years for multicellular life to appear, and another 500 million years for intelligence. But those timescales are not laws of physics. They are contingent on Earth's specific history. On a different world, with different selection pressures, intelligence could have arisen faster, or slower, or not at all. We do not know, but the possibility exists. Now imagine that intelligence did arise on ancient Mars. Imagine a civilization that built cities along the shores of that northern ocean, that looked up at the two moons, Phobos and Deimos, and wondered what lay beyond. Imagine they developed technology, perhaps not like ours, perhaps following entirely different principles, but technology nonetheless. And then imagine that civilization watched as their world died, the atmosphere thinning, the rivers drying up, the ocean freezing and then sublimating away into space. They would have known it was happening. they would have seen their world ending in slow motion over thousands or millions of years. What would they have done? Perhaps they fled if they had the capability. Perhaps they went underground into lava tubes and caverns where heat from the planet's interior could sustain them for a while longer. Perhaps they simply died as their biosphere collapsed around them. And if they did, what would remain? The surface of Mars is hostile to preservation in some ways, but remarkably good at it in others. There is no plate tectonics on Mars. The crust is static, ancient. Features billions of years old still exist, barely eroded, because there is no rain, no rivers, no grinding glaciers to wear them away. Only wind and the occasional meteorite impact. If something was built on Mars 4 billion years ago, parts of it might still be there, buried under dust, yes, but there, not melted back into the mantle, not subducted into an oceanic trench, just sitting there, waiting. And this is why Mars has become the focus of so much speculation. Because if anywhere in the solar system might still hold evidence of an ancient civilization, it is Mars. Of course, we have not found that evidence. The rovers and orbiters we have sent to Mars have found no cities, no roads, no unambiguous artifacts. But we have found anomalies, strange features that do not quite fit the expected patterns of natural geology. Most of these can be explained. Pareidolia, the human tendency to see faces and patterns in random shapes, accounts for many of the so-called structures that enthusiasts have pointed to in orbital images. A rock that looks like a pyramid is still just a rock. Wind erosion and volcanic activity can create remarkably geometric shapes, but not all anomalies are so easily dismissed. There are features on Mars that remain unexplained, not because they are artificial, but because we do not yet fully understand Martian geology. And in that uncertainty lies the possibility, however remote, that some anomalies might be more than they appear. The key is not to look for buildings or machines which would have been destroyed or buried long ago. The key is to look for techno-signatures, subtle clues that technology once existed, unusual concentrations of metals that do not occur naturally in the surrounding rock, isotope ratios that suggest nuclear processes, patterns in the distribution of minerals that are too regular, too orderly, thin layers of material that resemble industrial waste, objects in orbit, or debris fields on the surface that cannot be explained by natural processes. These would not be obvious. They would require careful analysis, detailed spectroscopy, boots on the ground, or at least very advanced robotic missions. But they would be detectable if they exist, and we have barely scratched the surface. The rovers we have sent to Mars have explored areas equivalent to a few city blocks on Earth. The rest of the planet, an entire world with the land area of all Earth's continents combined, remains untouched. Somewhere in those billions of acres of rust-red desert, evidence might be waiting. But Mars is not the only candidate. In fact, it may not even be the best candidate. Turn your gaze inward, toward the sun, and consider Venus. Venus today is hell. The surface temperature is hot enough to melt lead. The atmospheric pressure is 90 times that of Earth, equivalent to being a kilometer underwater. The atmosphere is almost entirely carbon dioxide, laced with clouds of sulfuric acid. Nothing we know of could survive there. The Soviet Venera probes that landed on Venus in the 1970s and 80s lasted only a few hours before being crushed and cooked. Venus is a cautionary tale, a runaway greenhouse effect taken to its ultimate extreme. But Venus was not always like this. In fact, for most of its history, Venus may have been the most Earth-like planet in the solar system. Models suggest that Venus might have had liquid water on its surface for as long as 3 billion years. 3 billion years, from shortly after its formation until perhaps 700 million years ago. Venus might have had ocean. It might have had a climate similar to Earth's. It might have been habitable. The runaway greenhouse effect that turned Venus into an oven likely occurred relatively recently in geological terms, triggered by volcanic outgassing that released massive amounts of carbon dioxide into the atmosphere. Once the process started, it was irreversible. The oceans boiled away. The water vapor, itself a greenhouse gas, trapped even more heat, which released more carbon dioxide from rocks, which trapped more heat, a feedback loop that did not stop until the surface was hot enough to glow. But before that happened, Venus had time, billions of years, far longer than Mars. If life could arise on Venus, it had a vast expanse of time to evolve, to complexify, to perhaps become intelligent. And if a civilization did arise on ancient Venus, what happened to it? Did they see the end coming? Did they watch as their world slowly became uninhabitable, as the temperatures climbed and the oceans began to steam? Did they try to escape, to migrate to other worlds, or did they perish, helpless, as their planet transformed into a furnace, and what evidence would remain? The surface of Venus is young, geologically speaking. Volcanic resurfacing has erased most features older than a few 100 million years, but that resurfacing is not total. Some highland regions appear older, less affected by volcanic flows, and beneath the surface, in the deep crust, evidence might still exist. Anomalies in mineral composition, unusual structures detected by ground-penetrating radar, artifacts buried under kilometers of basalt. We do not know because we have barely explored Venus. The surface is too hostile for long-term missions, and our orbital data is limited. But future missions, equipped with advanced instruments and perhaps floating platforms in the cooler, upper atmosphere, might be able to search more thoroughly, and if they find something, anything, that suggests technology once existed on Venus, it would rewrite our understanding of the solar system. But perhaps the most intriguing candidates are not planets at all. Perhaps the best places to look are the moons, the icy moons of the outer solar system, worlds covered in frozen water, hiding vast oceans beneath their crusts. Europa, orbiting Jupiter, Enceladus, orbiting Saturn. These moons are small, far from the sun, and bitterly cold on the surface, but beneath the ice, heated by tidal forces as they flex and squeeze in their orbits, liquid water exists. Oceans that may have existed for billions of years. And where there is liquid water, there is the possibility of life. Now imagine an intelligence arising not on the surface, but in the depths, a civilization that never saw the stars because they lived under kilometers of ice. A civilization that built cities in the abyssal darkness, powered by hydrothermal vents, illuminated by bioluminescence, entirely unaware of the universe beyond their frozen ceiling. Such a civilization would be almost impossible to detect from space. They would leave no atmospheric signatures, no industrial emissions, no electromagnetic radiation. They would be invisible unless we drilled through the ice and sent probes into the ocean. And even then, their artifacts might be scattered across a seafloor larger than Earth's Atlantic Ocean, buried under sediment, corroded by billions of years in cold, dark water. Finding them would be like finding a needle in a haystack the size of a continent, but that does not mean they are not there. Titan, Saturn's largest moon, presents another possibility. Titan has a thick atmosphere, thicker than Earth's, and lakes and seas of liquid methane and ethane on its surface. It is cold, far too cold for liquid water, but it is dynamic, active, with weather and erosion and a complex organic chemistry. Life as we know it could not exist on Titan's surface. But life as we do not know it, life based on different chemistry, using liquid methane instead of water as a solvent, that is speculation, but not impossible. And if such life could exist, could it become complex? Could it become intelligent? The timescales are available. Titan has existed in roughly its current state for billions of years. And if a civilization arose there, it would be so alien, so fundamentally different from anything we understand, that we might not even recognize its artifacts as artificial. A methane-based technology might look nothing like ours. No metals, no combustion, no electronics as we know them, just strange structures in the haze, patterns in the chemistry of the lakes, anomalies we cannot explain. And then there are the asteroids, thousands upon thousands of them, most no larger than mountains, drifting in the space between Mars and Jupiter. They are airless, lifeless, bombarded by radiation and micrometeorites, but they are also stable. An object placed on an asteroid would remain there, essentially unchanged for billions of years. No weather to erode it, no geology to bury it, just the slow accumulation of dust and the occasional impact. If an ancient civilization wanted to leave a message, to create a time capsule that would survive the ages, an asteroid would be an ideal place to put it. And some asteroids have shapes that are unusual, not impossible, not definitely artificial, but unusual enough to make you wonder. Oumuamua, the interstellar object that passed through the solar system in 2017, had an elongated shape that sparked speculation. Most likely it was a natural object, a shard of rock or ice from another star system. But it accelerated slightly as it moved away from the sun in a way that was not entirely consistent with outgassing from a comet. Probably natural, probably. But the fact that we are not certain, the fact that we had to seriously consider the possibility that it might be artificial, tells you something about how little we know. So, let us talk about time, about how long things last, because this is the crux of the question. If a civilization existed 1 billion years ago, what would remain? Our intuition, shaped by human lifespans and historical timescales, tells us that things endure. The pyramids have stood for 5,000 years. The Colosseum, 2,000. Surely 1 billion years is just more of the same, scaled up. But it is not. 1 billion years is not a longer version of human history. It is a fundamentally different kind of time, a time in which the very rules of what persists and what dissolves are alien to our experience. Steel, the backbone of our civilization, corrodes. In the presence of oxygen and water, iron oxidizes, rusts, and eventually crumbles to powder. Even stainless steel, given enough time, will succumb. How long would a steel building last? In a dry, stable environment, perhaps a few thousand years before it became structurally unsound. In a humid environment, less. Buried under sediment, protected from the atmosphere, it might last longer, but the metal would still oxidize slowly, reacting with minerals in the surrounding rock. After 1 million years, a steel structure would be unrecognizable, reduced to a stain of iron oxide in the geological record. After 10 million years, even that stain would be dispersed, mixed with other sediments, lost. Concrete fares little better. It is durable on human timescales, but it is not immune to time. Water seeps into cracks, freezes, and expands, breaking the material apart. Chemical reactions between the cement and the environment slowly degrade the structure. After a few thousand years, concrete begins to fail. After 100,000 years, most concrete structures would have crumbled. After 1 million years, they would be rubble, indistinguishable from natural rock formations. Plastics, paradoxically, are both incredibly durable and incredibly fragile. They do not biodegrade easily, which is why they accumulate in the environment today. But they do break down under ultraviolet light, fragmenting into smaller and smaller pieces, microplastics, nanoplastics, until eventually they are dispersed at a molecular level. Buried in sediment, protected from sunlight, plastics could last for tens of millions of years, perhaps longer. They would be detectable as anomalous organic molecules in ancient rock layers. But they would not look like plastic. They would look like strange hydrocarbon signatures requiring advanced chemical analysis to identify. And even then, you would need to know what you were looking for. Our satellites, the thousands of objects we have launched into orbit, are often cited as the most durable remnants of our civilization. Objects in high orbits, above the drag of the atmosphere, could remain in space for millions of years, but they would not remain intact. Micrometeorites, particles no larger than grains of sand, traveling at kilometers per second, would slowly sandblast them. Solar radiation would degrade their materials. Eventually, they would be reduced to clouds of debris, scattered along their orbital paths. After a few 100 million years, most satellites would have decayed, either falling back to Earth or being ejected from orbit by gravitational perturbations. A few might persist longer, in very stable orbits, but they would be unrecognizable, just fragments of metal and ceramic drifting silently through space. Even nuclear waste, one of the most persistent products of our technology, has a finite lifespan. The isotopes we create in reactors have half-lives measured in thousands or millions of years, but not billions. Plutonium-239, One of the longest-lived isotopes we produce in significant quantities has a half-life of 24,000 years. After 1,000,000 years, it would have decayed through dozens of half-lives, reduced to trace amounts. After 1 billion years, it would be gone, transformed into stable lead and other elements. The only signature that would remain would be an unusual ratio of lead isotopes in the rock, a subtle anomaly that might be attributed to natural processes if you did not know what caused it. So what does last 1 billion years? Certain minerals, diamonds, zircon crystals, some forms of quartz. These are essentially indestructible on geological timescales. If an ancient civilization used synthetic diamonds in their technology, those diamonds might still exist, scattered through sedimentary layers, waiting to be found. Certain chemical signatures, isotope ratios that do not occur naturally, spikes in rare earth elements, anomalous concentrations of metals like platinum or iridium, thin layers of sediment with unusual compositions. These are the kinds of traces that could survive 1 billion years. Not buildings, not machines, but whispers, faint chemical ghosts of a technological past. And this brings us to the methods, to the ways scientists would search for evidence of an ancient civilization if they were looking. The first and most obvious method is to look for structures, artificial shapes, regular patterns, things that are too geometric, too orderly to be natural. On Mars or Venus or the moons, this would mean high-resolution orbital imaging, looking for anomalies in the landscape, straight lines, right angles, repeating patterns. But this is difficult because nature can create surprisingly geometric shapes. Columnar basalt, formed when lava cools and contracts, produces hexagonal pillars that look almost artificial. Wind erosion can carve rocks into pyramidal shapes. Tidal forces can create linear features in ice. The challenge is distinguishing between natural processes and intelligent design, and that requires not just images, but context. You need to understand the geology of the region, the history of volcanic activity, the patterns of erosion. You need boots on the ground, or at least very sophisticated robotic explorers. The second method is to look for energy signatures. Any technological civilization uses energy, and using energy leaves traces. On a planetary scale, this might mean anomalous heat signatures, regions that are warmer than they should be, based on solar heating and internal geologic activity. In the geological record, it might mean evidence of large-scale combustion, spikes in carbon isotopes that suggest massive burning of organic material. On Earth, the Industrial Revolution is visible in ice cores as a sudden increase in atmospheric carbon dioxide and various pollutants. If an ancient civilization on Earth or Mars or Venus went through a similar industrial phase, that signature might still be detectable in ancient ice, if any remains, or in sedimentary rocks. The third method is to look for isotope anomalies. Nuclear technology, whether fission reactors or fusion processes, produces isotopes that do not occur naturally or alters the ratios of isotopes in ways that natural processes do not. On Earth, the atomic age is visible in the presence of isotopes like plutonium-239 and cesium-137, which did not exist in the environment before we created them. If an ancient civilization used nuclear technology, those isotopes would have decayed by now, but they would leave behind daughter products, stable isotopes in unusual ratios. Finding those ratios would require detailed spectroscopic analysis of rock samples, looking for patterns that do not match natural radioactive decay chains. It is painstaking work, but it is possible. The fourth method is to look for unnatural minerals. Certain materials do not form naturally, or form only under conditions that are extremely rare. Synthetic diamonds with unusual impurities, alloys that do not occur in nature, ceramics with compositions that suggest high-temperature industrial processes. If an ancient civilization manufactured these materials in large quantities, fragments might still exist, scattered through sedimentary layers. Again, this requires knowing what to look for and having the tools to analyze samples at a microscopic level. The fifth method is to look for orbital debris. Objects in space are not subject to weathering or erosion, at least not in the same way as objects on planetary surfaces. If an ancient civilization had a presence in space, some remnants might still be there, slowly drifting through the solar system. These would not be intact spacecraft or satellites. They would be fragments, pieces of metal or ceramic, perhaps no larger than pebbles, but with compositions or structures that suggest artificial origin. Detecting them would require dedicated surveys, looking for objects with unusual orbits or unusual spectroscopic signatures. It is a needle in a haystack problem, but not an impossible one. And the sixth method, perhaps the most speculative, is to look for patterns in the arrangement of natural objects. If an ancient civilization wanted to leave a message that would survive for billions of years, they might not build a structure. They might instead arrange natural objects in a pattern that could not occur by chance. Imagine a set of asteroids whose orbits form a geometric figure when viewed from a certain angle, or a distribution of craters on a moon that encodes a mathematical sequence, or a pattern of mineral deposits on a planet that spells out a message in a universal language, like the digits of pi. This sounds like science fiction, and it probably is, but it is also the kind of message that would be essentially immune to geological processes. The objects themselves are natural, so they do not erode or decay. Only the arrangement matters, and if the arrangement is stable over long timescales, the message persists. But here is the uncomfortable truth. We have not been looking, not really, not systematically. The search for extraterrestrial intelligence, SETI, focuses on electromagnetic signals from distant star systems. It looks outward to civilizations that might exist light years away, broadcasting their presence across the galaxy, but it does not look inward to civilizations that might have existed here, in our own solar system, billions of years ago. And why would it? The assumption has always been that if such civilizations existed, we would have found evidence by now. But that assumption is based on the idea that evidence would be obvious, that ancient cities would still be standing, that artifacts would be lying on the surface waiting to be picked up, and we now know that assumption is wrong. Evidence would not be obvious. It would be subtle, ambiguous, easy to overlook, and we have only just begun to develop the tools and methods needed to search for it. The absence of evidence, as the saying goes, is not evidence of absence. It is evidence only that we have not yet looked carefully enough. Mars, a planet with the land area of all Earth's continents, has been explored by a handful of rovers that have collectively traveled a few dozen kilometers. Venus, with its hostile environment, has been visited by only a few short-lived landers. The icy moons of Jupiter and Saturn have been observed from orbit, but never explored up close. The asteroids are mostly uncharted. We have sent probes to a few, but the vast majority remain unvisited. The solar system is immense, and our exploration of it is still in its infancy. To declare with certainty that no ancient civilizations existed because we have not found evidence is like walking into a library, glancing at a single shelf, and concluding that the library contains no books. And then there is the question of what finding evidence would mean. What would it do to us, to our understanding of ourselves, to know that we are not the first, that other intelligences arose, built, created, wondered, and then vanished, leaving only faint traces in the rock? It would be humbling, certainly. It would shatter the idea that we are unique, that intelligence is a rare and precious thing that arose only once in the history of the solar system. But it would also be strangely comforting. It would mean we are not alone in deep time, that others have walked this path before us, that the spark of consciousness and curiosity that drives us to explore and create is not an accident, not a fluke, but something that the universe generates given the right conditions and enough time. Or imagine the opposite. Imagine we search systematically and thoroughly and find nothing. No anomalies, no isotopes, no structures, no debris, nothing. What would that mean? It would mean that in 4.5 billion years, across an entire solar system of worlds and moons and asteroids, intelligence arose only once, here, on this small, blue world. That would be extraordinary in a different way. It would mean that whatever chain of events led to us, from the first self-replicating molecules to the first multicellular organisms to the first brains capable of abstract thought, was vanishingly rare. That we are, in fact, alone, not just now, but throughout the entire history of the solar system. And that would place an enormous weight on our shoulders, because if we are the only ones, then what we do matters in a way that is almost unbearable. We are not just one more species, one more experiment in evolution. We are the universe's first attempt, in this corner of space, to know itself. And if we fail, if we destroy ourselves, or fade into extinction, there may be no one else to carry the torch. Both possibilities are profound. Both change everything, and we do not yet know which is true. But we are beginning to develop the tools to find out. Missions to Mars are becoming more sophisticated, with plans for sample return missions that will bring Martian rocks back to Earth for detailed analysis. Missions to Venus are being planned, with the goal of studying the planet's surface and atmosphere in unprecedented detail. Missions to Europa and Enceladus are in development, with the aim of searching for signs of life in their subsurface oceans. And as our instruments become more sensitive, as our understanding of geology and chemistry and planetary science deepens, we will be able to search not just for life, but for techno-signatures, for the faint echoes of civilizations that might have come before. The search will not be easy. It will require decades, perhaps centuries, of careful exploration and analysis. It will require patience and rigor, and a willingness to consider possibilities that seem unlikely, even absurd. But it is a search worth undertaking, because the question of whether we are the first is not just a question about the past, it is a question about the future. If we are not the first, then we must ask why the others are gone. What happened to them? Did they destroy themselves in war or environmental collapse? Did they transcend, leaving the physical universe behind in ways we cannot yet imagine? Did they simply fade as their stars died or their worlds became uninhabitable? And whatever the answer, what does it tell us about our own chances of survival? If we are the first, then we must ask what that means for the civilizations that might come after us. If intelligence is so rare, so difficult to achieve, then we have a responsibility, not just to ourselves, but to the future, to ensure that the flame we carry is not extinguished, to leave behind not just ruins and chemical traces, but knowledge, wisdom, a roadmap for those who might follow. To be the first is to be a pioneer, and pioneers have a duty to those who come after. In the end, the question is not really about ancient Martians or Venusian empires or civilizations hiding beneath the ice of Europa. It is about time, about the vastness of it, about how much can happen in 1 billion years, and how little of it we understand. We live in a moment, a brief flicker of awareness in the deep dark. Behind us stretches an unimaginable expanse of time, filled with events and processes, and perhaps even stories that we will never know. And ahead of us stretches another expanse, just as vast, just as unknown. We are somewhere in the middle, looking backward and forward, trying to make sense of it all, and the possibility that others have stood where we stand now, have looked up at the stars and wondered, have built and dreamed and ultimately vanished, is a reminder of how precious and fragile this moment is. We do not know if we are the first, but we do know that we are here, now, with the ability to ask the question. And that alone is worth celebrating, because whether we are the first or the latest, we are part of a story that is still being written, and how we choose to live, what we choose to create and preserve, will determine whether that story continues, or whether we too become just another faint trace in the rock, a mystery for some future intelligence to ponder.